Okay, so last time we talked about determinant forms, and we showed that if we got something of the form 0 over 0, or infinity over infinity, or one of the other indeterminate forms, that was basically insufficient to determine what the value of the limit was. But there are cases where you do get something that's undefined, and it happens to not be one of these indeterminate forms, but actually is a determinant form, in which case we get an infinite limit. So we've talked about infinite limits before. If we take something like 1 over x, you'll notice that if we consider the limit as x approaches 0 of 1 over x, we found that this was infinite. And again, I also mentioned last time that we kind of were a little bit lax as, whether we consider it a plus infinity or a minus infinity. And again, depending on the context of the class that you're taking, you might need to make that distinguishment. But you have to remember that saying that a limit is equal to infinity is really just a way of saying that a limit does not exist. But to be specific about this being an infinite limit, if we consider just the table of this function, I start plugging in 1 for x, you'll notice that as x gets closer and closer to 0, f of x gets larger and larger. And of course, you can put negative signs in front of all of these too, and these will be negative. And of course, that's how you get this graph. So notice, especially as you approach from the right, as you get closer and closer to 0, these y values attend to this vertical asymptote here. And likewise here, we get negative infinity. Again, sometimes you need to make the distinguishment between positive and negative infinity. Many times, though, you do not. So how can we generalize this to not just 1 over x, but to anything? Well, it turns that we have a determinant form of something that's an infinite limit. So the idea here is if we attempt to do direct substitution on some function, and we get something of the form c over 0, in which c is not equal to 0. So let's say we get something like 3 over 0, or negative 5 over 0, or something of that sort, okay? That's going to indicate to us that our limit is going to be plus or minus infinity, okay? So let's do a quick example to see how this works. So we've got a rational function here, and we've dealt with situations where we plug the value and we get 0 over 0, we got to factor and cancel. But in this example, if we try to plug in 1, so we're going to get 1 squared minus 1 plus 5 over 1 minus 1. The numerator simplifies, and we get 1 minus 1 plus 5, which is simply 5, and in the denominator we get 1 minus 1, which is equal to 0. So we do not get 0 over 0, we get 5 over 0. And when this happens, we can conclude that this limit is infinite. Okay, so now suppose we do want to consider, well, is it plus or minus infinity? There are a number of ways to deal with that. Usually one of the simplest ways, because again, this isn't a real limit. You have to understand that this is a limit that does not exist. And again, depending on the class you're taking, you might even just say that the limit does not exist. Maybe you'll put plus and minus infinity. Or maybe you'll need to consider, well, is there one-sided behavior, two-sided behavior? I usually find the easiest thing to do is to simply graph the function and get that information that way. So as you can see from the graph here, if I consider the limit as x approaches 1 from the left of this function, which I could copy it down, you'll see that we get negative infinity. So from the left is over here. And then if we consider from the right, we get that it is positive infinity. So that is a nice way to make that distinguishment if you need to make it. But that's pretty much all we need to talk about infinite limits at the time. So I hope you found this helpful, and as always, take care.